Let's start with a cosmic truth. The universe hates order. The second law of thermodynamics dictates that all closed systems inevitably will move toward maximum entropy. Over time, heat dissipates, structures break down, and everything perfectly ordered naturally degrades into chaotic noise. This physical law is the ultimate enemy of our modern infrastructure. Every time you save a file, you are fighting entropy. The binary hardware powering our servers relies on precise physical states that constantly generate heat, slowly degrading delicate materials until they inevitably fail. We entrust our entire civilization's history, economy, and scientific knowledge to digital servers. Yet the physical reality is that every hard drive currently spinning on Earth is slowly dying. No matter how advanced our engineering gets, our technological progress is bottlenecked by this simple rule. We are running a permanent, losing race against thermodynamic decay. You might think quantum computing offers an escape route. Quantum processors can solve extremely complex problems that would take traditional computers millennia, but they actually face an even more aggressive threat from thermal decay. The core issue is a process called decoherence. Quantum memory relies on qubits, which hold incredibly delicate, overlapping states of information. It only takes a tiny amount of ambient heat or stray electromagnetic noise to scramble that information, destroying the qubit's memory in mere milliseconds. We currently build massive sub-zero cooling systems and highly calibrated electromagnetic shields to protect these fragile states, but the environment always eventually leaks in. Protecting quantum memory from heat requires a phase of matter that is intrinsically stable, rather than relying on external refrigeration to stave off the inevitable noise. In 2012, Nobel laureate Frank Wilczek proposed a mathematical loophole. To understand his idea, look at an ordinary spatial crystal, like this translucent halide. Its atoms spontaneously lock into a rigid, repeating three-dimensional grid. Physicists call this breaking spatial symmetry because the atoms choose specific, localized positions rather than spreading out evenly in all directions. Because space and time are physically interconnected, Wilczek reasoned that if matter can spontaneously break symmetry across 3 dimensions, it could also do so across the 4th dimension of time. The result is a theoretical phase of matter known as a time crystal. Instead of its physical structure repeating in spatial dimensions, its atoms periodically oscillate and repeat their movements in a continuous loop through time. This means you have a physical object that ticks naturally, entirely on its own, without requiring a battery or a wound-up spring to maintain its rhythm. At first glimpse, a time crystal looks like a perpetual motion machine, which violates the laws of physics. But here is the trick. The crystal's repetitive oscillation happens while the system is sitting entirely in its quantum ground state, which is its absolute lowest possible energy level. Because it has no excess energy left to lose to the surrounding environment, it generates no heat. Its internal entropy remains perfectly flat and stationary, satisfying the laws of thermodynamics by simply refusing to increase. This chart shows how researchers actually build these structures today using Floquet systems. They hit a highly isolated quantum setup with a periodic external driving force, like a continuous rapid sequence of laser pulses. In 2021, Google's quantum AI team successfully demonstrated this on their Sycamore processor. As you can see on the bottom line of the chart, the simulated time crystal absorbed none of the laser's energy. Instead, it rigidly locked into a subharmonic frequency, ticking away at a slower, perfectly fixed fraction of the laser's rhythm. By achieving motion without energy transfer, scientists successfully engineered a space where matter moves without transferring energy, essentially putting the rules of entropy on pause. Observing a time crystal inside a highly controlled quantum processor is a massive scientific achievement, but to build real-world memory drives, you need to be able to physically interact with the crystal to write data without shattering its delicate state. Recently, researchers at Aalto University tackled this exact problem. They engineered a new time crystal using quasi-particles known as magnons, which they submerged in a bath of superfluid helium-3 cooled to a fraction of a degree above absolute zero. This diagram shows the scale of their milestone. They physically connected this magnon time crystal to a standard mechanical oscillator. Rather than collapsing upon contact, the crystal's structure survived the mechanical surface wave continuously for several minutes. This successful physical interaction proved that time crystals possess a remarkable structural rigidity, allowing them to interface directly with traditional hardware components. This mechanical interaction provides the precision needed to write data, as the external wave leaves a distinct imprint on the time crystal's frequency. Compare this to standard qubits, which lose their data to the slightest thermal noise in a matter of milliseconds. Time crystals provide an architecture for ultra-stable memory that actively rejects environmental interference. The applications extend far beyond data storage. This resilient state of matter provides the foundation for highly efficient quantum batteries that don't leak energy over time, and ultra-precise frequency sensors capable of detecting gravitational waves. These laboratory successes demonstrate a path toward anchoring our most vulnerable digital information within a perpetual temporal loop, shielded from the noise of the surrounding universe. In a universe strictly governed by chaos and physical decay, human engineering has designed a clock that entropy simply cannot stop.